This program is brought to you by Stanford University.
I want to come tonight to the idea of inflation. Inflation is an important idea in cosmology, maybe one of the most important, and sort of at the root of much that we know, much that we suspect about cosmology. But before I do, let me remind you about what the presence of a cosmological constant does in Einstein's equations. The cosmological constant, I'll remind you, is just a term in the energy which doesn't dilute as the universe expands, an energy density which does not dilute. So it's just a term in Einstein's equations. Einstein's equations are the same as the Friedmann-Robertson-Walker-Lemaitre equations. A dot over A squared is equal to the energy density, and I'm going to take the case of flat space, although we may want to modify that later, the case in which space itself is flat, not space-time, but space. And in that case, what goes here is just 8 pi over 3 times Newton's constant times the energy density. And in general, the energy density may dilute. The energy density or mass density, we discussed various cases. There was the case of matter-dominated, where rho was just the mass energy of a collection of particles that are expanding. Because it's expanding, the energy density decreases. And in that case, rho goes like 1 over a cubed. We studied the case where rho was radiation energy. That's what dominates in the very early universe. It was 1 over a to the 4th. And we also talked about vacuum energy. And in vacuum energy, rho is just constant. Right? So we can just call that rho naught, or we can call the whole thing on the right-hand side lambda, or something proportional to lambda. There's some definition of lambda, the cosmological constant, which includes, I forget how many 8s and pi's and so forth. But this whole right-hand side would be a constant then. All right, let's suppose this is a constant. Let's call this constant, let's just give it a name, h squared. Why am I calling, and h is a constant. It does not change with time. That's the nature of vacuum energy. The nature of vacuum energy is the right-hand side doesn't change. Of course, the reason I'm calling it h squared instead of just h is because the left-hand side is a square. And this will have the nice properties when I take the square root. It will say that a dot over a is just equal to the constant h, where h is the square root of the vacuum energy times g times 8 pi over 3. That's square root of 8 pi g over 3 times the vacuum energy, rho naught. Rho naught just means vacuum energy. So if you know the vacuum energy, then you know h. As I emphasize, h is a constant, right? And then a dot over a is just equal to that constant. This is a special cosmology that has nothing in it but vacuum energy. Now, remember also that a dot over a is also the Hubble constant. So for this very special case where there is nothing but vacuum energy, that is a special case, when there's nothing but vacuum energy, the Hubble constant is truly constant. It doesn't change with time. If the Hubble constant doesn't change with time, what does that say about A? Well, we can write it as A dot, which is dA by dt, is equal to this constant, Hubble constant, times A. And the solution to that equation is an exponential. The rate of change of the scale factor is proportional to the scale factor with a constant of proportionality just equal to h. And the solution to this is A is equal to some constant. It doesn't matter. We can just ignore what the constant is and write e to the ht. In other words, the scale factor, or the distance between distant galaxies, unbound galaxies, galaxies which don't have enough gravity to between them to keep them from receding, the distance grows exponentially. That space-time which is exponentially expanding in that manner, is called de Sitter space. It's just a very simple solution of Einstein's equations with a positive cosmological constant. Incidentally, I've assumed that the vacuum energy here is positive. Right? Could it be negative? Yeah, it could be negative, but in fact, let's take the case where it's positive, the vacuum energy density is positive, then this is the solution, and when I say it's the solution, I mean to say that the geometry, d tau squared, is equal to dt squared minus a squared, which is minus e to the 2ht, that's a squared, times dx squared. And the dx squared means dx squared plus dy squared plus dz squared.
How can it be negative? You have a positive quantity on the left-hand side.
Yeah, yes, you're right. It can't be negative and space be flat. It can be negative if space is not flat. For example, there is the curvature term here, plus or minus 1 over a squared. But you're right, the whole thing here has to be positive in order that the left-hand side be positive. But this can be negative and this be positive, and something else happen. But let's not belabor that, because we're going to take it to be positive in any case, the vacuum energy to be positive.
Einstein put his cosmological constant in to make sure that the universe wasn't expanding. Is that how he did it? Is he just...
Well, what he did was to say, we know that there's ordinary energy in the universe, so let's put in plus some constant m over a cubed. And then thought about the possibility of cancellation between this and this.
Oh, so he put rho naught equal to minus m over a cubed.
Yeah.
Okay.
It was a misstep. It didn't make sense. Right, but that's why he introduced it in the first place. Okay. In any case, this geometry which exponentially expands, distance between any 2 points exponentially expands, it has a constant Hubble parameter, is called de Sitter space. Discovered by the Dutch astronomer Wilhelm de Sitter very shortly after Einstein invented his theory, long before it was known that the universe was expanding. And it's an important space-time in cosmology. It's important for two distinct purposes. One of them is the explanation of the currently accelerated universe. Acceleration, what does acceleration mean? It just means that the second time derivative of a is positive. Let's go back to this simple, this case over here. This, of course, would be called an unaccelerated universe because the second time derivative of a is just plain 0. This is accelerated because the second time derivative of a is positive, and in fact growing with time. All right, so that's the accelerated universe. It's an observed fact. Today, this is a correct description of our universe. Not quite, and not quite because there is some additional energy besides just the vacuum energy. So let me just remind you quickly what we know from observations. We know that the scale factor in the past was this usual t to the 2/3. That's the matter-dominated universe. And then at some time of order a few billion years ago, somewhere more or less at the halfway point between now and the Big Bang, it began to exponentially increase, or it began to increase more rapidly. Now, t to the 2/3 doesn't look like that, does it?
Curvature's wrong.
Yeah, curvature's wrong. T to the 2/3 look like that. Convexity is wrong. Right. And then at some point, it did start to look like that. And we're somewheres over here. So this is an observation. This is not something which is speculation. And there's enough of this curve here that's been measured that it does fit neatly on to the exponential. It itself, of course, is not quite an exponential because it's a transitory behavior, but it appears to all observers tend to agree. It looks like it's entering into an exponential phase, right? Which is another way of saying that the vacuum energy is bigger than the other energies, roughly by a factor of 2 today, but this is getting smaller and smaller with time, and this is not getting smaller and smaller with time. So that's our current understanding of the universe today. It's exponentially growing. It's de Sitter space. And the Hubble constant, which is not exactly constant today because it's not exactly exponential, but is tending to an exponential. All right, that's today. It is also worth discussing the idea of a horizon. I think we've done this before, but let's do it again. It's an important idea. At some relative coordinate spacing, let's call it delta x, or at some let's not coordinate spacing, at some distance, some actual proper distance, using Hubble's law, we can calculate the velocity as a function of that distance, and at some distance it becomes equal to the speed of light. All right, remember that distance times Hubble is equal to velocity, and so if we want the velocity to be the speed of light, then the distance that we have to go out to is equal to the speed of light divided by that Hubble constant, the Hubble constant being the square root of the vacuum energy density. The smaller the vacuum energy density, the smaller h, the bigger the distance to that place where things are receding away from us with the speed of light. That place, of course, is called the horizon. And if you like, it's a sphere around us at a distance given by c over h. Numerically, it's about 10 or 12 or 15 billion light years, which accidentally happens to be about the same as the age of the universe. Now, whether that's an accident or not is a matter of very intense argument. But they're two different quantities. One is the age of the universe. In other words, the time, where is it? I threw away my graph, but there it is. Universe started and did this, and we're over here. Okay. So, as it happens, this distance scale, apart from a factor of the speed of light, is about the same as the age of the universe. So the distance is about 10 or 12 billion light years away. And at that distance, as I said, this, yeah.
I was to say, isn't Hubble, isn't the tangent line to the, at any point, if it happens to intersect the origin, then those two quantities will coincidentally be the same. In other words, distance to the horizon and
That, of course, would be exactly true for A of t equals t. Right. Right. Yeah. Okay. So at the moment, it is a bit of a mystery why the vacuum energy happens to be such, okay, that the distance to the horizon, or converted to a time by means of the speed of light, why the distance to the horizon is about the same as the distance to the surface of last scattering, but if you like, to the age of the universe. Not known exactly why that's true. It's a coincidence as far as we know.
Well, it's not remaining the same either, is it?
Which is it?
The horizon is remaining.
The Hubble constant is remaining the same. Of course, the age of the universe is not remaining the same. Right. Right. So it sounds like it's a coincidence of just us being here at the time that we're here. Right. Let's take it to be just a coincidence. Now, is it a coincidence? Is it a coincidence that the Darwinian timescale for evolution happens to be the same as the timescale as obtained from the vacuum energy? No, that's clearly something which we have to explain someday.
In the Sitter space, is that assuming that there's no matter and no radiation?
Yeah.
Okay. Now,
Absence of this term completely.
when we did the Einstein equations, we had a situation where so I guess there's a form of energy, this can you say something about this vacuum energy? Because I'm pretty confused about what its source is or what it is. I mean, you would think that if you didn't have any matter or radiation, you'd get nothing. I mean, naively.
Right. So for that, we have to understand why quantum mechanics gives energy to the ground state of systems. The vacuum is the ground state of, let's say, quantum field theory. Ground state means the state of lowest energy. Now, in the vacuum, it's possible to have oscillations of electric and magnetic fields and so forth. The oscillations behave like ordinary oscillations. And ordinary oscillations have a ground state energy. The ground state energy is not zero. And the reason that it's not zero is because of the Heisenberg uncertainty principle. We're going off track, but let's answer the question anyway. If we have a harmonic oscillator, that's the potential of a harmonic oscillator, the energy of it is proportional to the momentum squared, that's the kinetic energy, I'm not going to put in numerical factors, plus the distance squared that you stretch the spring, so to speak. All right, there's usually a factor of spring constant here and a factor of 1 over twice the mass here, but just leave it like this. This is good enough for us. P squared plus x squared. Now, classically, the ground state of the harmonic oscillator simply means the configuration in which the spring is at its equilibrium point, not vibrating, not stretched, just sitting at its equilibrium point. X equals 0, and because the velocity of it is also equal to 0 at the equilibrium point, P is equal to 0, and the energy is equal to 0. P squared plus x squared, both of these terms are equal to 0. The Heisenberg principle does not allow there to be a state in which both x and p are simultaneously knowable, in the language of quantum mechanics, diagonalizable. And so there's a necessary fluctuation. If x were literally right at the center here, then p would have to have an infinite fluctuation. If p were at the center, in other words, if the momentum was exactly equal to 0, then x would have to have an infinite uncertainty. And so there is no state of the system in which both p and x are exactly known to be equal to 0. They both fluctuate. But the sum of p squared plus x squared doesn't necessarily have to fluctuate, but it's got to be positive. Since both p and x cannot simultaneously be 0, the vacuum or the ground state energy of a harmonic oscillator is not 0. Now what is it? What is the ground state energy of a harmonic oscillator? 1/2 h bar omega, where omega is the frequency of the oscillator. Now, the universe is full of potential harmonic oscillators. Full of harmonic oscillators. They're the oscillations of the electromagnetic field. There's in fact an infinite number of them, of low frequency, high frequency, and a large number of such oscillations, not just the electromagnetic field, but every field. And every field has a ground state energy. It's the energy stored in that field due to 0-point oscillations. Every field behaves like an oscillator. Every field has 0-point energy, and it's those 0-point energies which are one explanation of the vacuum energy. The real puzzle is why it's so small. It is very small, numerically very small, but that is not for tonight. Let's just recognize that it exists. As the universe expands, it doesn't dilute. It's just a constant. And experimentally, it really is, or observationally, it really does seem to be there with a particular numerical constant, which happens to be extremely small, measured in natural units.
I have an idea. Why isn't that just the last scattering baseline energy?
I don't know what that means.
I just mean that there's always 3-degree.
No, it's not the 3-degree radiation. That's radiation. That energy decreases with time because the photons dilute. And furthermore, each photon decreases its energy. It's not the 3-degree. It's the oscillations that are there when you remove all the real photons. It's the virtual photons, or just the 0-point oscillation that is necessarily present. Of course, we're not now talking about a particle on the end of a spring. We're talking about the fluctuations of the electromagnetic field. In fact, do you know what these two things would be for the electromagnetic field, for which there's an uncertainty principle?
Well, isn't this like sourceless?
B and E.
B and E. B and E.
What?
Electric and magnetic fields. The energy of an electromagnetic field is E squared plus B squared, with E being like momentum and B squared. And there's an uncertainty principle between electric and magnetic fields, which is very similar to the uncertainty relation between velocity or momentum and position. Okay? So they can't both simultaneously be zero because of an uncertainty relation between them. And the result is that even when you remove as much energy as is possible to remove from the field, there's still this residual 0-point energy. That's what constitutes, or at least that's what's believed to be the origin of this.
I'm still having a tough time understanding. If you remove matter and you remove radiation, what causes the electric fields? Like, what's the perturbation and what?
I can't answer what causes it. I can tell you that the uncertainty principle requires it to be there.
But we're making the assumption there is no electric field, there is no mass. Oh, I thought you...
Did I say there's no electric field?
So de Sitter space has only the dark energy. Or
right.
Okay.
It has no real photons. It has only the 0-point energy.
Okay, you can have an electric field without real photons.
It just doesn't have any charges.
It's there anyway. The field fluctuates anyway. It doesn't need charges.
Right.
Yeah.
Can you go over that point about the age of the universe being equal to the surface?
Inverse Hubble constant?
Yeah.
Okay, let's take a
I know it's equal to inverse Hubble constant, but it's also equal to the distance to the surface of last scattering or something?
Oh, that's an approximation, that it's the distance to the surface of last scattering.
But
He said it was equal to.
isn't that just a mathematical truism? Just because of the equations? It's just it's not an experimental fact?
Almost, yeah.
But not that H is approximately the age of the universe.
No, clearly it does not have to be. In this de Sitter space, it's simply not true. H just never changes. The age of the universe does change. It's exactly true. It's only exactly true for this scale factor over here. Let's see why. All right, let's take this case. A of t grows like t. then what is H? H is equal to A dot over A. What is A dot? A dot is 1, and T and A is T. So this is just equal to 1 over T. And it's clear that the Hubble constant, it's not constant, but the Hubble parameter is just 1 over the time from the Big Bang.
That's true for any T to the P.
Any power law, well, it's not quite true. Take any power law here. Then it becomes, then A dot is equal to P, T to the P minus 1.
Yeah.
And then divide that by A, that means dividing it by T to the P, and the answer is P over T. So for example, if P is 2/3, then this would be 2/3 over T. And it would not quite be the case that the Hubble constant was 1 over time, but it would be 1 over time with a factor of 2/3 in front of it.
Yeah, but I'm assuming there's other constants we're not including anyway.
All right, that's right.
Should be 3 halves in front of it. H should be 3 halves 1 over T.
Did I write 3
Yeah, 1
halves?
over P, so it's...
No, that's right. 2/3 is right, but H is...
2/3 is right. Okay. Yeah, 2/3 is right. That's H. Left-hand side is H.
For the de Sitter universe, it's infinite.
Wait. H is equal to 2 over 3 T, where T is the age of the universe at any given time. Okay. Now let's come to the de Sitter case. The de Sitter case, it is not T to the P. It is E, it's exponential. E to the HT. Let's not call it H, okay? Let's just call it E to the constant, gamma T. All right? A is E to the gamma T. What is A dot? Incidentally, I could put a constant in front of it. It wouldn't make any difference. Let's put the constant in front of it. What is A dot? A dot is C gamma E to the gamma T, right? Just differentiated E to the gamma T. Now divide it by, that's A dot, divide it by A, which is just C, that cancels C, and it cancels E to the gamma T. So we find out that the Hubble constant now is truly constant, and it's just as gamma, which appears here. Okay? This is the unique case in which the Hubble constant is constant. It's the only case where it's constant. And once we know that that A dot over A, let's go back, A dot over A is equal to the square root of 8 pi g over 3 times rho. This is the square root of the FRW equation. All right. So the Hubble constant is just the square root of 8 pi g over 3 times the vacuum energy. That's H. All right, so there's a definite connection between this vacuum energy on the one hand and the Hubble rate of expansion. We call this sometimes the rate of the Hubble rate of expansion. It's the thing that goes in here. It tells us, in this case, 1 over h is not the age of the universe. What is it? It's the time constant. It's the time that it takes the universe to double, not double in size, but multiply by e. Yeah. The time that it takes for the universe to double, I said double again. Let me use double, but I really mean multiply by e. It's the time constant for the universe to double in size. And what is that? That is the inverse of this h, and it's about 10 billion years. Okay, so every 10 billion years, we can expect the universe will double in size, roughly speaking. That's an approximation.
Could I ask you a question?
Yeah.
This vacuum energy density is constant, right?
Yeah, it's constant. Well, yes. This, of course, is an experimental question.
Okay, so if the universe is expanding, so that implies to me that the energy, the total energy, vacuum energy, is increasing. Where is it coming from?
It's coming from the other side of the equation. This minus this is equal to 0. This is one form of energy. This is another form of energy. This is a kind of kinetic energy of expansion. It's a kind of kinetic energy of expansion. Both terms appear in the expression for the energy in general relativity. And it's conserved because it's equal to 0. So this energy is coming from here.
Does that come from then all these particles originally?
That comes from Einstein's field equations. If you apply the ideas of Hamiltonians and energy to Einstein's field equations.
No, but we talked about all that kinetic energy at the beginning of the universe, right? So is that basically being transferred? Is that kind of?
Yeah, it's a transfer of kinetic and potential energy. Yeah.
When we talk about energy being conserved or entropy increasing, are we talking...
Entropy or energy?
Either one.
Okay.
Are we talking about that within the cosmic horizon, or do we mean including outside the cosmic horizon also?
Okay. The cosmic horizon is fixed in size. It doesn't change with time. That's the same statement that the Hubble constant doesn't change with time. The energy within the cosmic horizon stays fixed with time. The vacuum energy is just the volume of this times the vacuum energy density. The vacuum energy density, which is rho naught, let's work it out. Okay, so that's this diameter here, which is, what is it? C divided by square root of 8 pi g over 3 times the square root of rho naught in the denominator. That's the distance. Now what do I want to do with it? I want to cube it in order to find the volume. Cubed. Yeah, 4/3 pi. Okay. And then multiply that by the vacuum energy density, and the vacuum energy density is rho naught itself. There's some amount of energy in there, but it doesn't change with time. It doesn't change with time, the amount within the cosmic horizon. So the portion that we can see, the portion that we can ever see, that energy doesn't change with time. If it's de Sitter space, right, if it's de Sitter space. Right. So, standing here from our vantage point and looking out and looking at all the vacuum energy that's out there, no, it doesn't change with time, the portion that we can see. Okay. Good. So that's the basic idea of a cosmic horizon. Things can pass through the cosmic horizon in the same sense that they can pass through a black hole horizon. And I won't go into that in any depth now, but once they do, they're out of contact with us and they're gone.
Can I just follow up with a question? So if it's not a de Sitter space, does that mean that energy flows outside the cosmic, the energy within the cosmic horizon?
It might. Well, energy is a loaded term. Exactly what do you mean by the energy in general relativity? In general relativity, the concept of energy is a little bit curious because it contains this gravitational component as well as ordinary energy. This is the gravitational component of the energy here for this particularly simple kind of geometry.
You want to get on to the rest of the stuff?
Yeah, let's move on. All right, now the same mechanism appears to have happened in the remote past, but instead of the time constant being about 10 billion years, it was about 10 to the minus 32 seconds, or perhaps that fast. Where does this come from? Well, the origin of the question, this is inflation. This is the idea of inflation. The universe in the remote past exponentially expanded. Now, when I say this happened, of course, to some extent, this is conjectural, but the conjecture has passed a number of observational tests. So when I say something has happened, you can feel free to put a little bit of a question mark. Did it really happen, or am I guessing? Okay. So I will tell you what's known and what the empirical evidence is, but let me just shorten my sentences by saying something happened. All right. happened that in the remote past, before anything that we can observe, in other words, out beyond the surface of last scattering, or earlier than the time when the universe became transparent, the universe was exponentially expanding. Now, why did that idea gain any traction, and where did it come from? Well, the basic place that it came from was the flatness of the universe. To make a long story short, spatially, the space slices of the universe are rather flat. Flat meaning we don't seem to live in a curved universe which is either positively curved or negatively curved. We seem to live in a very flat universe. In fact, not only a flat universe, but a rather homogeneous universe. On large scales, bigger than superclusters of galaxies, in particular on the largest scales, the universe is very flat and homogeneous and smooth. How did it get to be that way, and why is it that way? The early ideas of the Big Bang were that the universe started just in some random state. It could have started with some very complex geometry. It didn't have to be flat, and it didn't have to be homogeneous. We don't really have a theory of how it began in the very, very beginning. But let's suppose it began like a shriveled up raisin or prune with all sorts of wiggles and texture to it. Where did all those wiggles and texture go? Where did it disappear to? Now, in fact, we know, here's something we know. We know at the time of the surface of last scattering, in other words, at what we ordinarily think of as the Big Bang, the beginning as far as we can see back, already at that time the universe was very flat and smooth. So it's not that it flattened itself out and stretched itself out between the Big Bang and now. Big Bang, I mean, looking back to the surface of last scattering. The surface of last scattering itself is very smooth, which indicates that at the time when the universe was as hot as the surface of the sun, it was already very smooth. So something had smoothed it out. Now, you might say, why do you need something to smooth it out? Just postulate that it started out smooth. Okay, you can do that. But in fact, it wasn't exactly smooth. We'll come to the deviations from smoothness, but the question was asked, why is it that the universe started so very smooth? Why is it that the density in one place is about the same as the density in a very, very different place? In particular, we can imagine places which are so far apart that light, we can see them both. All right, we can see them both. We see something way out there and something way out there, but we know that light did not have time to get from one to the other. So there was no way that a smoothing process could have happened on such large scales. And what is it that made the universe smooth and flat on those scales? Well, the hypothesis is that what we ordinarily call the Big Bang, that there was a prehistory to it. And during the prehistory of it, the universe exponentially expanded by an enormous amount and got itself stretched out to be almost completely flat, like the inflation of a balloon. I like to think of it that way. You start with a completely deflated balloon, and the completely deflated balloon looks like a you know what a completely deflated balloon looks like, okay? It has all sorts of wrinkles, a wrinkly balloon, a really wrinkly balloon. Right? And now you start blowing it up. And after it's expanded a certain number of times, it gets pretty homogeneous. It gets pretty smooth. Okay? So if there was, and this prehistory would have had to be before the surface of last scattering, because it's known it was already very smooth at that time. All right? What was the hypothesis? The hypothesis was cold inflation due to Alan Guth in the early 80s, around 1980, that the universe underwent at that very early time a period of exponential inflation, exponential growth. In other words, that for a period it behaved like de Sitter space.
Are we assuming equilibrium before inflation?
No. 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 Whatever inflation does, it stretches things out so much that you lose memory of what the structure might have been like before inflation started. It just takes whatever was there and stretches it out so much that it just leaves it in this very, very homogeneous configuration.
There was no previous homogeneity.
We don't know. We don't know. One of the good thing about inflation is it erases all the initial conditions, and so you don't have to know what the initial conditions is, because you don't have to know what the balloon looked like in the beginning, because it gets stretched out. The bad thing about inflation is it erases all the information about how it started.
I don't know. I mean, if you had a blotch on a raisin and you blew it up, and you would still have a blotch.
No, you're blowing it up to something very much bigger than the size of the known universe. So imagine there was a blotch on the raisin, and the raisin got to be 10 to the 10 to the 10 to the 10 times bigger than the observed universe, exponentially. Remember, the idea was it was exponentially growing. So it got to be 10 to the 10 to the 10 to the 10 to the 10 times bigger than the observable universe.
So it's just as if the surface becomes transparent from previously opaque or something.
It's not transparent. It just gets stretched out. It just gets stretched out so that that blot or that blob, that little bit of inhomogeneity got stretched out. It's still there, but it's there on a scale much, much bigger than we can see. Okay?
But you have to assume that it wasn't sort of a fractal to start, right? Because in that case, you wouldn't even,
Yeah. You had to assume that, that there was smoothness on some terribly tiny scale. But if the universe expanded enough, if it inflated enough, then if you start on any scale with some fluctuation, it will eventually stretch that fluctuation out. That's known as inflation. And the hypothesis is that in the very early universe, that basically exactly the same kind of thing happened that is happening today, except with a Hubble constant at that time, which was millions and millions of times larger. In other words, with a vacuum energy which was very much larger than the vacuum energy that we see today. Okay, now that's a curious idea. It's a crazy idea. Why was the vacuum energy different then than it is now? Can we even call it the vacuum energy if it had to do with something which is different than the vacuum today? And what's the basic idea? All right, so the basic idea goes something like this. Now we do have to talk. I'm going to tell you what the idea is, and then we'll come back at some point, I hope, and discuss what the empirical evidence for this idea. At first, it was just almost a throwaway idea. Maybe something like this happened. And as time went on, observation got better and better to the point where this picture has been pretty well confirmed by now. That doesn't mean it's absolutely got to be right. It means that it's the best candidate for our understanding of what happened. All right, to understand, you have to have the idea of a scalar field. A scalar field is a field, just like Maxwell's field, just like electric and magnetic field, except instead of being a vector at every point in space, the electric and magnetic fields are vectors. They have direction at every point in space. It's just a scalar. No sense of directionality. And let's call that field, let's give it a name, let's call it phi. Is it any of the fields that we see in nature today? Is it identified? Are its quanta identified with any of the known particles? Definitely not. Definitely not. It is not identified with any observed field that we know about in physics, and its quanta are not identified with any known particles. So it's a hypothetical field which exists and fills space in the same way as any other field. And it has an energy. It has an energy associated with it. The energy that's associated with it is a kind of potential energy. And a potential energy that scalar fields can have and it's a potential energy, V, which the V is standard terminology for a potential energy. It doesn't, when I say it's a potential energy, I mean it doesn't have to do with the time derivative of phi. Of course there's energy in a field if it's oscillating, if it's fluctuating, but there also can be energy in a field just because the field is displaced away from zero value. When phi, now this, for the moment, let's completely forget about quantum mechanics. Quantum mechanics is not important to the discussion right now. And it's some potential energy called V of phi. V of phi is some function of phi. Let's just draw some picture of it. Here's some picture of it. Any function, whatever function you like, you can put in here, and of course you get a different theory out no matter what function you put in here, but imagine some function of phi. Then if phi is one value or another value or another value or another value, the field energy, and it's a kind of vacuum energy, it's a kind of energy that's there not really in the vacuum, but there simply by virtue of having some space in which there is a field which takes on a particular value. It's very similar to vacuum energy, V of phi, but it can vary.
Can I ask a question about that drawing? Is that, what's the horizontal axis is
Phi.
Phi, and the vertical axis is
V.
Okay.
Right. All right. Now, you're buying a whole set of ideas here, which none of which are obvious. First of all, that there can exist scalar fields in nature. This is not obvious. That they have potential energy. Well, the mathematics of field theory suggests that they can and do have potential energy. And the potential energy can vary from point to point, so different values of the field can have different energies. All right. But one also has to take it as a matter of, you have to take it as a matter of faith. I take it as a matter of known mathematics, that V of phi, if phi is not changing, for example, if it just has some value over here, is a kind of vacuum energy. It's a kind of vacuum energy which doesn't dilute. That's the main property of it, it doesn't dilute. This part of the energy of a field doesn't dilute. Yeah.
If you drew a picture of space, then would phi be constant over the space?
It may or may not be constant.
So then it could have different values?
Yeah, it could have different values in different places. That's right. Let's for the moment suppose that it was the same everywhere. Let's take that case for the moment. All right, we take that case for the moment. And we say, what would the world be like?
Phi itself is a function of x, y, z, and t?
In principle, it could be a function of x, y, z, and t. Let's take the case for the moment where it's just constant for whatever reason, at some value of phi. Then, in effect, the world has a vacuum energy which is just V at that value of phi. That's the way scalar field energies work. They behave exactly like vacuum energy. In particular, they don't dilute. So then, if that were the case, we would simply say that the vacuum energy is replaced by V of phi, where phi is the value that the field happens to have. It might be over here, it might be over here. As long as it's not changing with space or time, it would just be a constant, phi being constant in space. And then we would go back to all the equations for de Sitter space, or all the equations for the expansion of the universe, and every place we saw rho naught, we would stick V of phi. In particular, the universe would expand with a Hubble constant, which would be equal to the square root of 8 pi over 3 g, and instead of rho naught, I would write V of phi. Now what happens if V of phi, if phi varies from place to place? Supposing over here it's a different value than it is over here, or a different value than it is over here. Well, first, let's go back to the case where it's not varying. What's happening where it's not varying? The region of space over which it's not varying is expanding exponentially like e to the ht. What happens if it varies from place to place? Then in different places, it's expanding with different time constants, but stretching exponentially by an amount that depends on v at every place. So if v is varying, or phi is varying from place to place, you would have exponential expansion everywhere, but a different time constant in each place. Right? But if the universe expands enough, if it inflates enough, if it stretches enough, and you're inside there someplace, and you can only see out to your horizon, eventually the stretching is so much that your entire environment has been stretched out to the point where the field within your region has become homogeneous, has become constant. So it's very much like this balloon. If the balloon could be painted with some color which varies from place to place, red over here, blue over here, purple in between, and then you expand it out, inflate it out by many, many orders of magnitude, and somebody at the center, or somebody at some point who only can see so far, sees a very homogeneous color. All right? Same thing with this inflating universe. V might vary from place to place, but if it does vary from place to place, it will get stretched out in such a way that, that it will look, for practical purposes, as if it were very constant. Now,
it would worry me, though, if phi varied, let's say, very proportional to something. In other words, it's not, what you seem to have drawn is a situation where phi is constant in patches, and it seems to me like it could be,
it doesn't have to be constant, just slowly varying.
Slowly varying.
Slowly varying. Slowly varying on what scale? Well, it doesn't matter much, because whatever scale it's slowly varying on, eventually that scale will get stretched out. Now, you could imagine maybe it was so bad to begin with that it would never stretch out. You could imagine that, but apparently that's not the way it was. And that we judge because the universe is today rather homogeneous. All right. So let me draw for you then the way experiment, various combinations of observations, suggests this v of phi to be. Oh, yeah, all right. Incidentally, if you have a potential energy function which looks like that, it could be the potential energy, instead of for a field, it could be for a coordinate of some kind. What happens if you start the coordinate over here? What happens if you start a particle in a potential energy and you start over here? You roll down. Now, let's suppose you start up here. You roll down, you roll over the hill, you roll over the hill, and you eventually go somewhere else. If there's a lot of friction, you might roll down the hill here and just get stuck at the minimum. The minimum really are places, the minima really are places where the field would just be constant. If you started the field over here, it really wouldn't be constant. It might roll down. If there was friction, and there is friction in cosmology, if there was friction, then it might just come to rest at the bottom over here. If it comes to rest at the bottom, if the field comes to rest, then it's constant. That's the situation in which you can pretend that the field is very constant and doesn't change with time if it's sitting at the minimum of the potential. It could come to rest in any of these. All right, so here is what it is thought, that the potential energy of some field, which we have never discovered, we've never measured it, it is a conjectural, speculative construction with a field energy with a V that looks something like this. Now, perhaps it starts with a shape of some unknown kind, but then it gets very flat. Not completely flat. Question? So the field energy doesn't vary for very much over some range of phi. And then all of a sudden it comes to the end of a cliff, and falls down. It doesn't quite go to zero, and then turns back up. Now this is so ridiculous that so contrived, let's put it this way, it is so contrived that it almost seems quite ridiculous. Nevertheless, this is what observational cosmology seems to demand. So here's the picture. The universe started in some unknown way, in a way that we don't know, with a field energy v of phi that was located on a plateau like this. Because this was almost a flat plateau, phi didn't change very much with time. It changed very slowly, like being on a very, very shallow, like this eraser on the tabletop here. There's enough friction, and in fact in cosmology there was a lot of friction. The eraser doesn't move very much. You could tilt the table quite a bit before you would start to move off. The kind of friction is not quite the same as the kind of friction on this table here. Yeah, more like a viscosity. Yeah, more like a fluid viscosity. This is called slip-stick friction, which means it sticks until it slips. All right. Motion of an object through a liquid or gas is a better analog for what happens for cosmology. So, but there is a kind of viscosity. Viscosity is the right picture. There is a kind of viscosity that's particularly associated with an expanding universe. And the faster the expansion, the bigger the viscosity. And so if this were a particle moving on a potential energy surface like this, in other words, just a potential like this, it would slowly, slowly, slowly move down here under the combined effect of the slope of the potential. That means a little bit of a push in this direction, and at the same time the viscosity would keep it moving slowly. It would stay at this level for a long period of time. During that time, V didn't change much. So V was almost constant during that time, and if V were constant, then it would just be a constant vacuum energy. So to the extent that the universe slid down this hill very slowly, and the vacuum energy didn't change much, then during that period, the universe inflated. During that period, the universe exponentially grew, and it exponentially grew with a time constant that looks like this, where V of phi was just the value of V along here.
A very big value, right?
What's that?
A very big value.
Well, it depends on what units you're measuring it, of course. So if you're measuring it in ordinary, everyday units, it's enormous. Even if you're measuring it in elementary particle units, it's very, very large. But if you're measuring it in Planck units, it must have been, it was very small. So it depends on what units you're talking about. But in units, anything like the density of energy in this room, it's humongously big. Right, so very, very large energy here.
What's causing phi to move? What's causing phi to move? It's changing
the slope of the potential.
Okay.
The slope of the potential is causing it to slowly drift down that hill, roughly as if you had a weak gravitational field. Forget talking about ordinary gravity. Imagine this room were filled with liquid, filled with honey. Okay? And you put a rock in it. The gravitational field would correspond to a tilt in the potential energy. Potential energy higher at one end than at the other end. Higher up there than it is here. The viscosity of the honey would lead to the rock falling, and it would fall slowly with a terminal velocity. All right, so this slowly slides down here, assuming the slope is small enough, until it gets to the edge, and at the edge here, it suddenly goes over the edge and winds up eventually down here. Okay, what does eventually mean? Eventually means today.
Isn't that more like slipstick?
No. No, it doesn't. It never sticks.
Well, I mean,
It doesn't
it
stick.
looks like it's slipping.
It's slipping. No stick, though.
Right, it's not just a station.
Right. I always thought a slipstick was a thing, but a slipstick wasn't a thing. A slip was slip or stick.
Slide rule. A slide rule, slipstick.
Do they call it that? Yeah. So they do, okay. Okay, yeah, I guess from my engineering background, I thought a slipstick was a thing. But no, it's an adjective, slipstick friction. All right, it's not slipstick, it's just slip, or viscosity. And then when it gets to the end here, all of a sudden, the potential energy changes rapidly. That means effectively that there's a large force on the universe pushing it over the hill here. And what happens when it gets down here? When it gets down here, at the minimum, it comes to rest. It comes to rest, a combination of friction and minimum potential energy, it comes to rest. All right, where are we today? We're down at the bottom. How do I know what the height of this potential energy is? Because I know today what the Hubble constant is. So the Hubble constant is 8 pi 3 over g via phi. That's the exponential growth of the universe today. And that appears to be down here. The coefficient down here is very, very small, much, much smaller than it was up here. Why this is true, we don't know. We really don't know. But we do know what the potential energy is at the bottom here, because we know today what the Hubble constant is, today. All right? And it's very small. We also suspect, and there's some evidence, that the potential energy up here was very much larger, and that the Hubble constant was very much larger. In other words, that the doubling time of the universe was many orders of magnitude larger than this one doubling every 10 to the 10th years. In fact, with standard cosmological numbers, this inflation took place with a time constant of 10 to the minus 32 seconds or something like that. So it's kind of crazy. I mean, this is a crazy picture. This is a crazy picture. The amazing thing is that it seems to have some validity. Right? We gradually drifted down here and came to the edge and went down to here. The expansion that took place up in here is called inflation. It's called inflation. Where did the Big Bang happen, incidentally? The thing that we normally call the Big Bang. The Big Bang happened after we got pretty much down to here. After we slid over this edge, the Big Bang, meaning to say, what I mean by the Big Bang now is the surface of last scattering. The surface of last scattering was very late in this picture. It happened well after the universe settled down here. So the Big Bang and everything we actually can observe about cosmology was down in here. Right? But before the Big Bang happened, this period of exponential inflation took place, according to theory. And during that period, the universe stretched itself out so much that all of the wrinkles disappeared, if you like. So that means that the universe at the time of the Big Bang, or the time of the surface of last scattering, was already stretched out by many, many powers of E. How many powers of E? That we don't know for sure. You were going to ask a question.
The wrinkles are mainly wrinkles in this primordial scalar field, then.
And also the gravitational field. Also the gravitational field, yeah. In other words, the shape of space and its curvature might have been fluctuating, but also phi. Okay, yeah.
What is the x-axis? Is that t or is it phi?
Phi. Here, in this? Phi, the field phi. This is the potential energy as a function of the field phi. The field phi can depend on time as the universe rolls down this hill.
Well, it's sort of acts like a time parameter.
Like a what?
It's acting like a time parameter here because you've got a monotonic function that it's...
It is, in fact, acting like a time parameter. This is true. Time parameter meaning to say that it's monotonic function of time. Yeah.
What is the part of the graph after that minimum?
What's it again?
What is the part of the graph after that minimum?
Here?
Yeah,
Who knows?
Or you don't,
Who knows? All we know is that we're living at some place where the potential energy is not quite zero. Yeah. Nothing in our experience tells us very much about here. Looking back in the past, we discover something that looks like a motion like this. We're going to come to what the observational evidence for this is, but
this may be a bad analogy, but when you're looking at gravitationally derived potential energy, it's a function of position, but there's only potential energy in the presence of a gravitational field. Weightlessness, there is no.
Okay, a gravitational field, simply in this context, means a gradient of the potential energy.
Well, what is the analog of a gravitational field in this picture? Or is there one?
Okay, let's not get ourselves confused between gravity as the real thing in this universe and the model that I was describing of a rock falling through honey. Right. 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 Some force on a system which pushes it from one place to another, basically. Right? That's the gradient of the potential energy here, the fact that it's not actually exactly flat. Just in case it was not clear, this was not intended to be exactly flat. It was intended to have a small slope. It's analogous to the table having a small slope. If the table has a small slope, then the potential energy differs from point to point. And if something is on this table, if there's no friction, what happens if there's no friction? It starts accelerating. Okay? What happens if there's some viscosity? It reaches a terminal velocity. It starts to accelerate, but then reaches a terminal velocity and just moves slowly across the table. If the table has a small tilt, it will move slowly. Okay? It will move slowly until it gets to the edge of the table. Okay? And then it falls off.
So it doesn't oscillate through there?
Well, it may oscillate down at the bottom here.
How can we observe that?
That's dark energy, dark matter. But, all right. The Big Bang and everything we historically know about the universe all took place after this got down to very close to the bottom here.
And where's today?
Also down at the bottom. It fell down this and just stuck there. Not stuck because of stick slip, but stuck because it's the minimum of the energy.
And what is the period of inflation where this balloon is expanding? Is that just the cliff or the whole thing?
No, the whole thing here.
And that's about t to the minus 32 seconds.
That, right.
10 to the minus 32 seconds.
Doubling every 10 to the minus 32 seconds. Now, that may seem very fast, but on the scale, on the Planck scale, in units of Planck time, it's very slow, in fact. The Planck time is 10 to the minus 42 seconds. This is... Yeah, right. We don't know how long this was, and so we don't know how long this inflation took place. So we don't know in that sense whether it expanded by a factor of 10 to the 10 to the 10, 10 to the 10 to the 10, 10 to the 10 to the 10 to the 10 to the 10. We don't know. All that information got wiped out by this expansion. Now, what happened? What did this expansion do? It did exactly the same thing that it would do to a balloon. It flattens it. And it leads to a situation where by the time you get to here, incidentally, falling off the edge here is called reheating. there's nothing re about it. It should just be called heating, but it's called reheating. Why is it called reheating? This happened rather suddenly. When a thing like this happens rather suddenly, the energy that was stored in the field is rather quickly converted to some other form of energy. When you fell off the cliff here, just like that eraser when it hit the floor there, its energy, its potential energy was converted to heat. Then as you roll over the edge here, and by the time you get down to the bottom, the universe is hot. It wasn't hot up here. In fact, any heat that might have been there to begin with was diluted by this enormous exponential factor. So if there was some thermal energy to begin with, the universe simply expanded so much that it got diluted to the point of almost
so that's why it's reheating. That first curve up there represents an injection of heat.
Well, or something. Right, right. But we also know, we know nothing about that. Right. It's you're perfectly right that perhaps in the very early prehistory something happened over here that was heating and then reheating, but we know nothing about this really. We can't observe this directly. All right, we can't, it's hard to observe. We don't know if we can observe it, but
we don't think it's lower.
Right, right. So how the universe got up here, why it started up there, we don't know. But we know that if it did start up here and it stayed up there long enough, that the initial conditions are sort of wiped out, or they're diluted so much that we have no fossil memory of them. Everything started very, very stretched out, which means the universe was extremely homogeneous. Now, this is going to be qualified. We're going to qualify the statement. I'm oversimplifying a little bit, sort of on purpose. If the universe expanded by a factor of 10 to the 10 to the 10th, then it would look extremely flat by the time you got to here. That's the reason we believe that the right solution of the cosmological equations today involves flat space. Remember, I told you earlier on that observationally, the curvature term, this factor k, which can be plus or minus 1 or 0, is observationally 0, meaning to say that the universe looks spatially flat to about 1%, or better than 1%, but it seems to be spatially very, very flat. Geometry of space seems to be Euclidean geometry. Why is this so? Well, to the best of our knowledge, there was a period of expansion which flattened everything out, so that we are today looking at the universe on a scale which is very much smaller than its curvature. We might as well use flat space because the universe radius of curvature is so much bigger than the region we can see. All right, now.
Question?
Yeah.
When you say 10 to the 10th, or is that just an arbitrary number, or do you mean it at least that big?
We don't know. We don't know anything about how long we remained up here. We don't know how wide this plateau is, and we don't know how shallow it is. The shallower it is, and the higher we actually don't know how high it is. We don't know how broad it is, and we don't know how. All right, we have some bounds. We have some bounds. We know something about the combination of these parameters, and basically what we know is that the universe doubled or got multiplied by a factor of e at least about 50 times.
Do we know
e to the 50th?
E to the 50th.
Okay. Do we have any idea how much energy got put in to the system?
We have some bounds on it. We have some bounds on it. That's another way of asking what the height of this is. Yeah. Yeah, we have some bounds on it. I would say the best bet would be something like about 10 to the minus 14 in Planck units, but that's a huge amount of energy in ordinary units. So you want me to give it to you in joules? Well, I can't give it to you in joules without sitting down and doing a calculation, but it's 10 to a large number, 10 to the 90th or something.
Why did the universe reheat after the expansion slowed down?
Well, it reheated because it came to the edge of this cliff, and that potential energy was converted at first into kinetic energy of the motion of the field, just as this eraser, its potential energy got converted to kinetic energy. And then when it hit the floor, where did that energy go to? Well, it went into thermal energy. It went into thermal energy, and that thermal energy is the energy that the universe had at the Big Bang. Yeah.
You made some sort of comment about dark matter. Is some connection with dark matter there?
You could ask, might this field have oscillated here? That oscillation energy conceivably could be the energy of dark matter. It would get diluted. The energy of, let's not get into that. I did say that, but this is not the important lesson here.
Can you say anything about the actual value of phi at the present, which is to say at V minimum?
Of phi. Yeah. You mean this distance?
No, the value
of V or
right, okay,
V or phi? V is vertical, phi is horizontal.
What is the value of phi relative to rho zero?
No. No. V has the same units as rho zero.
Okay,
that's V. All right.
Is that the same as rho zero?
Exactly. That's rho zero.
Very small. Could you plot phi as a function of time?
Yeah. I could plot it, but let me just draw it instead. I mean, let me just put my finger on here to follow it. Maybe it came, we don't know very much about this, but it slipped down here and then very, very, very slowly inched along here. While it was inching along here, things were exponentially growing. And eventually it got to here and went. Perhaps it oscillated a few times at the bottom, but there was a good deal of friction at the bottom due to the expansion of the universe. And so eventually it just came to rest at the bottom.
And then T goes on, but P stays still.
Right. In other words, as when you get down to the bottom here, you've gotten onto this branch of things which is today's current de Sitter space behavior. Now, do we know for sure that it comes to rest here? No, but we know that it's moving slowly. So this is a model of what we know. We know fragments of this. We don't know the whole picture with any great certainty, but we know some fragments. We know, for example, that this is not zero. So the universe is exponentially inflating today, but with this very long time constant. We know that it was rather high over here, many orders of magnitude larger than it is today. And so the universe did apparently, I have not talked about the observational evidence yet, but the observational evidence indicates that along here, the universe grew by at least a factor of E. I said E to the 50. Usually it's quoted as E to the 60. But you can play with the numbers a little bit. So the universe is E to the 60 times bigger than it was over here, at least, at minimum. Now, how many times, incidentally, the number of times that it got multiplied by E is called the number of E-foldings. E-foldings, an E-fold simply means multiplication by E. Each of which took 10 to the minus 32 seconds. But that number is dependent on the height here, and the height is not well known. The height is not well known. What's known is that there was at least about e to the 50 or more e-foldings. Sorry, 50 or more e-foldings. No.
Is it possible that that it was flat on the top and that there was just sort of the perturbations of the field which flipped it off the edge?
If it's too flat on the top, yeah. No, it's not consistent that it was completely flat. It had to have some tilt, but it could be pretty close to flat.
No possibility for some kind of quantum effect to flip it off to the flip it off the cliff.
Yeah. No, definitely.
So that you would just have sort of in this vast matrix of nothing, you'd have a universe here and a universe.
If it were too flat at the top, it would have created too inhomogeneous a universe, which was what I was about to explain.
Oh, okay.
Right. Okay, so we know that it couldn't have been too flat on the top. So let me explain how we know that. First of all, I said, this is an interesting story with many parts, and I will not try to get to them all now. But what I said was the universe inflates, and the process of inflating becomes homogeneous. Homogeneous on any ordinary scale. On a scale, let's say, as big as the horizon size. That's not terribly big. It may have had many more e-foldings than that. It may have been stretched out by many, many times bigger than that. In the same sense that the Earth is much bigger than the horizon that we can see from 6 feet above the Earth. Incidentally, what is the horizon from 6 feet above the Earth? A couple of miles, I think. Yeah. The Earth is much bigger than that. In the same sense, our horizon, not in the same sense, but in an analogous sense, our horizon is rather small on the scale of the radius of curvature of the universe, which means it expanded and inflated many times larger than the region that we can see. Okay, so it got to be, by this process of stretching, it got to be very, very homogeneous, except for one thing. One thing prevented it from becoming completely homogeneous, and that was quantum fluctuations. Quantum fluctuations. Now, we can delve into this a little more deeply, but not tonight. Quantum fluctuations created, just quantum mechanical fluctuations, take what would have become an infinitely stretched out, completely homogeneous universe and leave over quantum fluctuations of various wavelengths in here, which are the remnants of the quantum mechanical processes which took place. I will not try to explain them tonight, but let me just say that after this inflation took place, no matter how long it takes place, it never really gets completely settled down to complete uniformity. Why? Quantum mechanics. Quantum mechanics and quantum field theory ensure that there is always fluctuations. It's kind of an uncertainty principle thing again, but the fluctuations were there even after it may have expanded by 10 to the 10 to the 10 to the 10 to the 10 factor. There were fluctuations. In other words, the field was not completely homogeneous. It varied from place to place by an amount which was controlled by quantum mechanics. If there was no quantum mechanics, it would be completely flat. With quantum mechanics, it varies from place to place. Okay, now let's come to the central picture, which is really what has gotten the whole subject very exciting over the last 10 years. Let me draw, well, okay, here's the edge of the cliff. Let's draw that edge of the cliff over here. Here's the edge of the cliff. What I'm plotting here vertically is ordinary space X. What I'm plotting horizontally, what am I plotting horizontally? I guess, what am I plotting horizontally? the field, phi. What I want to draw is the contours of the field. The contours mean the surfaces of constant field, like a contour map. It's not a contour map of elevation, it's a contour map of the field phi. Now, if phi was completely homogeneous, it does vary with time. Here's what you would see. At one time, you would see a completely homogeneous field. That would mean that phi is the same at every point of space. Here's space vertically. Here's the field phi is horizontal. Phi is the same over here as it is over here, as it is over here, as it is over here. That means that phi has gotten very homogeneous. What would happen with time? As time transpired, as time went on, as transpired, you would roll down the hill, which would mean that the field would gradually moving to the right, until it got to the edge over here. When it got to the edge, that's the value of phi where reheating occurs. It would suddenly fall down, and a sudden change in phi where it would fall down to here. So with time, if you plotted phi as a function of position, it would be constant, constant a little later, constant a little bit later, slowly drifting to the right. And then, if it were all that homogeneous, in other words, all that smooth, every place in space would go over the edge at the same time, if it were completely homogeneous. But now let's put quantum mechanics in. What does quantum mechanics do? It puts some fluctuation into the field, and so we could expect that the contours will show some fluctuation. They will not be exactly homogeneous. And as we roll down the hill, some points reach the edge before other points. All right, here's the way I like to think about it. Imagine a bunch of soldiers walking in lockstep, arm in arm, and they're walking towards the edge of the cliff all together. If they are really very well lined up, with no fluctuation in the rank in their location, then they all fall over simultaneously. But what happens if some soldiers are slightly behind other soldiers? Some of them are a little bit in front, some of them are a little bit slow, and they're moving really, really slowly. Then there can be a long time delay between the time one fellow falls over and the time another fellow falls over. So there can be large gaps in the time between the time that the different pieces fall over the edge. Now, when you fall over the edge, when a piece of space falls over the edge, let's just take a very simple situation. Imagine the field is homogeneous except for a little bump. So the contour looks like that. It gradually drifts to the right. And this point over here falls off the edge before this point. So a region of space is created which has been reheated. It's down at the bottom here, whereas the rest of space is still up at the top of the cliff. All the soldiers except for one are up on the top. One guy has fallen over. Now that one guy has fallen over, that one region of space here is inflating less rapidly than the region up here. The vacuum energy down here is small. So it's inflating slowly down here and rapidly up here. What happens? What happens is the energy that's in here, the new energy that's in there, the kinetic energy, the energy of falling off the cliff here, is expanding less rapidly in space than the rest of this region out here. So a little lump of energy forms. A little bit later, let's say a little bit later, another bump goes over the edge. By the time this bump has gone over the edge, this one has been over for a while, and it has expanded somewhat. It has expanded somewhat, then the next one falls over the edge. What does this lead to? This leads to inhomogeneities in the energy density over here. It leads to inhomogeneities in the energy density because different regions went over the edge at different times, and their kinetic energies were expanded and diluted differently. There's a particular pattern to the kind of fluctuations in energy that take place, but what do these fluctuations of energy become eventually? These are the seeds of galaxies. The energy density is not uniform after you fall off the cliff, and in fact, the slower that you're moving, the bigger will be the inhomogeneities. If you're moving very, very slowly, then the time between this fellow falling over the edge and this fellow falling over the edge can be very large. During that time, this region may have grown, and then when the next one goes over, this one will have already spread out. So the energy density will be most variable in space if the field is moving very slowly.
It would seem it would be the other way, because the expansion slows down, so you'd go over, you'd expand less.
Oh, it has kinetic energy.
Yeah, it expands less.
Yeah.
Yeah.
And so that the first...
Yeah, no, that's right. So, yeah, but the point is that it will create variations in the energy density that will first of all come from the original variations in the field, but then magnified by this effect that one guy goes over before the next guy, and therefore the effect is different rates of expansion in the two regions, and that has the effect of making a variable energy density. That variable energy density is necessary. It's necessary because without it, there would be no galaxies. So it's a funny combination of inflating the universe and making it very smooth, but leaving over these little fluctuations which eventually became the seeds of galaxies. Now this is a highly quantitative story. I'm describing it descriptively, but it's something that can be quantitatively computed from the quantum fluctuations in a field and in expanding space, and you can compare it with the properties of the fluctuations which you can trace back from known galaxies, from known properties of the distribution of galaxies. You can trace it back to the earliest times right after this reheating took place, and it fits. It fits well, yeah.
Could you say that it was cooling, and that after it falls, it doesn't cool as fast?
No, that's not really quite right. It's a question of expansion that by the time this guy falls over, this guy is already spread out and done some expansion. No, it's not expanding as fast. That's right. So it's a combination. There's a competition of things going on. Expansion in this piece that fell over the edge, and the inflation of this other fluctuation here. And it gives rise to a pattern of fluctuations of energy density. That was, for all practical purposes, the observational start of the universe. Very homogeneous.
Let me ask it this way. The later fluctuations, are they hotter or cooler?
They're cooler. Well, they're cooler. They're cooler because they've been stretched somewhat. When this one...
The earlier ones are hotter than the later ones.
No, the earlier ones have cooled some. The next one that goes over, you see, when you go over the edge, if a little piece of space goes over the edge, it gets this much energy. All right, that much. Then that energy is diluted by expansion afterwards. So if a little piece of space, let's say that much space, goes over the edge, it picks up... Yeah, it's always hotter, right. All right, so then this one cools a bit, and then the next one falls over, and it's somewhat hotter.
Okay.
Yeah.
So the heat, so the hottest places are the last places to go
Yeah.
over the edge.
Yeah, so, that's right. But the main point is that it leads to inhomogeneities in the energy density. And those inhomogeneities, they're small, in fact. They were, I mean, observationally, the variations in the energy density are 1 part in 100,000.
This is dark energy variations, right?
No, this is primordial density fluctuations. This is neither dark. Dark energy is this.
Oh, okay.
That's the energy today.
But phi, you're saying, includes matter and radiation?
Yeah, that's right. It turns into all kinds of very hot stuff. Right. Matter, radiation, and that kind of stuff. And it varies from place to place. Observationally, about 1 part in 10 to the 5. Now, that 1 part in 10 to the 5 is not a number that we can derive from this picture. That 1 part in 10 to the 5 tells us some constraints on the shallowness of this, how flat it is, the flatness of it, the height of it. It puts some constraints on the parameters. Right. Once those constraints are imposed, then it creates a spectrum of fluctuations at different wavelengths, different size scales. These guys get spread out. This guy comes next. He's smaller in space and so forth. So the effect is that, that you have a fluctuation density spectrum, fluctuations on different scales. What happens to a variation in energy density that you start out with? Well, if you have a bit of overdensity over here, let's say overdensity, and a bit of underdensity over here, the overdensity gravitationally attracts material from the underdense region, and so the overdense region gets more overdense, the underdense region gets more underdense, and the effect is to magnify the spectrum of fluctuations. So just a very, very small little fluctuation to begin with will gradually build up, depleting the underdense regions and increasing the overdense regions. And that's the origin of galaxies. So from the spectrum of galaxies, from the distribution of galaxies in space, one can try to reconstruct the density fluctuations that were there at the very beginning. Now, the very beginning means after reheating, and compare them with the theory that this picture leads to, which is namely quantum fluctuations in the field being magnified by falling off the edge and then being processed by gravity. And the answer is it fits very well. It fits very well with this picture. And it's the only thing that fits very well with this picture.
So you have to assume that it's a fairly small volume at that point?
Where?
That the observable universe is a small volume?
At which point?
In galaxy formation.
Well, the time of galaxy formation, the observable universe was some pretty good fraction of what it is today. I'm not sure what you're asking.
Well, I'm just wondering how fast this movement from underdense to overdense takes place.
Oh, well, once it starts, it happens fast.
Is that during reheating?
No, that's after reheating. No, that's after, at the end of at the time of reheating, that's when these fluctuations were first established. In other words, after going over this edge here, there was some density fluctuations which were bigger than they were in here, but whatever they were. But still, 1 part in 10 to the 5, roughly. 1 part in 100,000. Yeah, it magnifies, by going over the edge, you magnify the quantum fluctuations, but then gravity still hasn't done its work. Gravity doing its work magnifies them more, and eventually magnifies them a great deal and turns them into galaxies and stars and planets and so forth.
Does that violate the second law? It sounds like it.
sounds like entropy is going the wrong way.
It's not. Gravity sometimes does things like that, has that effect. It tends to concentrate things, yeah. But it's not, no, it's not violating the second law. Nothing can violate the second law, but it looks somewhat counterintuitive in that gravity is rather peculiar from the point of statistical mechanics. Most things tend to make things flat and evenly distributed. Gravity tends to make things clump. All right? And the clumping actually increases the entropy. The ultimate is to clump them into black holes, and black holes really have a huge amount of entropy.
Yeah.
So, yeah.
How is the microwave background reflected in all of this? The lumps in the microwave background?
The lumps in the these are the lumps in the microwave background.
So mostly the mass doesn't really count that much. It's the microwave background that predominates here.
Well, no, it's that this stuff gets imprinted on the microwave background. So all of this structure evolved for a period of time. Gravity did not become important until after the surface of last scattering. Gravity only became important after the universe cooled down to below the temperature of the surface of the sun. So until that time, the fluctuations were pretty much primordial. Just these primordial fluctuations, and they imprinted themselves on the surface of last scattering, so that what we see in the sky in the surface of last scattering is pretty much these primordial density fluctuations.
Those regions have to be far enough apart that the thermal doesn't wash them out. The thermal radiation of before the surface of last scattering.
Yes, that's right.
You said that phi was a scalar field, so that wouldn't be an electromagnetic field.
No, it's not. Phi is not an electromagnetic field.
So how did all this? So the photons just went?
No, what happened is all of this energy. Look, what happens to that energy when that thing hits the floor there? Some of it gets converted into electromagnetic energy. Not very much, incidentally. Most of it just gets converted into heat. But the question is, what happened when this field fell down here? Okay. What could it get turned into? What can that energy get turned into by the time you settle down at the bottom? What could that energy be? The only thing it could be is particles of different type. That's the only other thing that we know that can carry energy is particles of different type. So in falling off the edge here, this field energy here presumably got converted into various kinds of particles. Those particles may have been unstable particles. They may have decayed. What did they decay into? They decayed into electrons and positrons, protons and antiprotons, or quarks and antiquarks, some photons. And when a large amount of energy is deposited like that, what does it do? It heats, it turns into heat. After a while, it just turns into heat. That heat eventually became the photons, electrons, positrons, protons, antiprotons.
So the reheating is actually where you get the manifestation of the...
is where you get what?
Manifestation of what?
Of matter inflation from... I mean, you're getting inflation of the universe.
Yeah.
But it's at that reheating point where it manifests as inflation in the mass and the particles.
Well, it's where it becomes particles. It's where that energy gets converted into radiation, particles, electrons, protons. The details of this are not known. The details of how you got from here to electrons, positrons, and so forth are not in detail known. The only thing you know is that when you have energy contained in a slowly expanding, and incidentally, once you got down here, the universe was much more slowly expanding. On the scale of the rapid particle reactions that take place, the universe was very slowly expanding when you got down to here. All right? So what happens if you take a bunch of energy and put it into a pot which is very, very slowly expanding? Well, it comes to thermal equilibrium. It somehow eventually equilibrates and turns into a thermal equilibrium, whatever the temperature happens to be. So the details of what go on as you go across here don't really matter much. All you know is a lot of energy was dumped into a pot which very, very slowly expanded. And that's enough to tell you that some percentage of it is going to be electrons, some of it's going to be positrons, some of it's going to be whatever it is.
Well, let me ask this. How much of physical theory survives going back behind the reheating? Pretty much gravitation and quantum field theory, but none of the other physical ingredients exist.
You mean up on the top here?
Yeah.
Right. That's pretty much right.
No photons, no particles of mass. And no particles at all, right? Because the Phi has no...
Well, the only thing that was there were these fluctuations, these quantum fluctuations in the fields. In particular, the quantum fluctuation in this field phi. And it's not worth calling them particles. Because,
so the actual act of the reheating, is that the cause of the Big Bang? Or
yeah, that's... yeah, you may, if you like, think of the reheating as the Big Bang. But it's still expanded many times over before it became the visible Big Bang. Remember, it was so hot when it went over the edge here. Energies here much, much higher than electron, positron energies and so forth. Much, much hotter than the surface of the sun when it went over here. So the universe was still very opaque. It had to cool down before it became transparent. So when we look out and see the surface of last scattering, that's very late on this scale.
Where is it on that graph?
It's down at the bottom.
That's where the last scattering occurred.
Yeah, down at the bottom. Everything that we can measure, see, observe, happened at the bottom.
Yeah. So by that stretch, then, when you have the quantum fluctuations, then there are really multiple big bangs, right? Each one, as it falls off, is causing...
Well, yeah, but, well, if you like. But on the other hand, these fluctuations are on scales anywhere from very, very much bigger than the horizon to anywhere much, much smaller. So some of these fluctuations were small enough in size that we see them manifested as galaxies and stars. Even planets. That's probably a stretch. Galaxies and stars. Yeah.
Wasn't there some discussion of acoustic waves and all this process doing some kind of stuff itself?
Yeah. Right.
I guess it has to do with the underdensity, overdensity.
Well, this happened. The acoustic waves are a phenomena that preceded the gravitational things. Yeah, we're going to talk about acoustic. I don't know. We have one more class. I don't know. All right. The acoustic waves are particularly interesting because they give us a measuring rod on the sky. All right. They give us the measuring rod, which, when we look out to the surface of last scattering. I will tell you about the acoustic waves the next time. You see lumps of stuff which were associated with acoustic waves, whose size you know. Where do you know them from? That I'll tell you next time. But because you know their size and because you know their distance, you can start looking at triangles. And it's those acoustic waves, which are manifestations of the processing of these fluctuations. They started to slosh. They basically started to slosh, and they created lumps, and the lumps are of known size because the laws of the acoustics and so forth are known. We know the size of them, we know the distance, and we can measure this angle. That's enough to use some geometry to tell us that space was either flat, positively curved, or negatively curved. And so those acoustic waves are important, and it's too late for them now. Okay. All right, do we have another class? I've lost track. We have one more? Two more? Two more. Two more? Okay, good. All right. So the next time I will tell you a little bit about how the geometry of space got measured from all of this.